Again, welcome to Mathematical Structure for Computer Science, CS113, also known as Discrete Mathematics. In these lectures, we're going to cover recursive algorithms, which cover Chapter 5, Section 4 of our course textbook. In our previous lectures, we discussed about recursive definition functions. So our main objective in these lectures is to go through recursive algorithms, which we have to use the concept of a recursion or recursive functions, how it works. In our previous lectures, we said recursive function have two parts, the basis and the recursive part also. So the same thing, if we are going to write an algorithm using recursion, then we must have the basis step and also the recursive step. So we'll see some few algorithms using recursion. And also we are going to prove if a recursive algorithm is correct. So first we start with the definition. But first, what is an algorithm? So we know algorithm will be a step-by-step task that we normally do to accomplish a function. Example would be, if I want to get ready to go to work, first thing I need to do is to take shower. Maybe when I wake up, maybe take shower, clean myself up before I put on my clothes. So algorithm is step by step in very sequential order. Now, if I want to get ready to work and I put on my clothes first before I take shower, well, the end result will not be good. I don't want to go to work with wet clothes on, or maybe there will be soap everywhere. So that's the concept of algorithm. Algorithm is solving a problem or performing any task by following some step in sequential order. First thing must be done first, second thing must be done second. And it have to be in a duration of time. There must be a time period to finish the task. So that will lead us to recursive algorithms. So recursive algorithm, again, is the same as algorithm, but this time we are going to use the recursive method to solve the problem. So the recursive method is the definition we have here. An algorithm is called recursive if it solves a problem by reducing it to an instance of the same problem with smaller input. So what we are trying to say is the recursive algorithm is an algorithm that normally reduces itself. So if I write a recursive function to solve a problem, the function must call itself by reducing up to the smaller input. And the smaller input normally will represent the basis step. Again, we went through recursion. Recursion have two parts. We have the basis step and we have the recursive step. So normally, if I'm going to find a factorial of a number, the basis step will be a factorial of 0 is 1, or a factorial of 1 is 1. That's the smallest input, 0 or 1. The reason why I'm saying 0 or 1, because a factorial of 0 or 1, the answer is the same, is 1. But we can choose only 1, let's say a factorial of 0. Now, if my question said I should find a factorial of 5, then in my recursive step, I will start from 5 times. The function will call itself by reducing 1. So it will be 5 times 4. It will call itself by reducing 1, 3. Call itself by reducing 1, 2. Call itself by reducing 1. Now, anytime we reduce by 1, we have to check with the base condition if the condition is true or false. Now, if the condition is true that our smallest unit is 1, then we stop. Then we give our final result that we have from the reoccurrence of the function, calling the function over. If it's false, then we keep calling out. That means we haven't reached the smaller input yet. So again, an algorithm is called recursive if it solves a problem by reducing it to an instance of the same problem. So a factorial of a number, you can see that we have 5 times 4 times 3 times. So it's like repeating the same thing, reduce it by 1, multiply, reduce it by 1. But if I want to find a product of a value that it will be 100 times 92 times 87 times 3 times 4, again, we can see that it's not the same. Anytime it's reducing, we are not doing the same task because the difference, the intervals are not the same. From 100 to 97 to 20 back to 5 and 6, we can use recursion. So for the algorithm to terminate, as we said earlier, the instance of the problem must eventually be reduced to some initial case for which the solution is known, which is the basis case. So example is given here, recursive factorial algorithm. So give a recursive algorithm for computing n factorial. Now, in computer science, we have something called looping or iterative. Now, I know a factorial of a number means I will multiply the number by itself, multiply the number to the next number by reducing by 1 all the way to 1. So, for example, if I'm looking for a factorial of 3, it's 3 times 2 times 1. Or I can say 1 times 2 times 3. This means I can use a loop to find a factorial of a number. Because when I have a loop, let's say I'm looking for a factorial of 10, I will say, okay, my loop will start from 1. And also it shouldn't go more than 10. We are going to start from beginning, not more than 10. Then we increment by 1. So now in my product, I will say the counter equal to the counter times whatever we start with 1. So first we initialize the variable factorial as 1. So 1 times the first value, then we increment the counter times the next value, increment the counter times the next value. So at the end, we're going to get 1 times, let's say if it's factorial of 10, then we get 1 times 2 times 3 times 4 times 5, all the way to 10. Here I'm using a loop, let's say for loop. Initialize my counter, I'll start from 1. And the condition will be this loop shouldn't go more than 10. So it should be less than or equal to 10. And we increment the counter. Let's say the counter name is I, so I say I equal to I plus 1. Then inside I have a variable where I will store my factorial result. Let's say we call the variable fact. So I can say fact equal to fact times I. And I'll initialize the fact to 1, the beginning, because 1 times any value is the same value. So when I start with 1, 1 times 1 is 1. Then we go to 2, 1 times 2 is 2. Then we go to 3, 2 times 3 is 6. Our result now is 6. We go to 4, 6 times 4 is 24. Our result now is 24. When we move to 5, 24 times 5 is 120. Then we keep going. So that's the way we solve a recursion problem using a loop. But now, I mean, this is how we solve a factorial problem using a loop. Excuse me, a factorial problem using a loop. So now, to solve a factorial problem using recursion, we need 2 things. We say we need a base and a recursive. So when we look at the algorithm here, we can see that here we are saying that if our input is 0, we return 1, which means if the factorial of 0, the answer should be 1. So this would be our base case. If n equal to 0, return 1. Else, return n times factorial minus 1. So if it's a factorial of 5, I would say 5 times 4. The result I get, we check. It's we reduce by 1. Is 3 equal to reach 0 yet? No. We go to 3. We go to 2. We go to 1. Then we go to 0. Is 0, then we stop. 0 give us 1. So whatever answer we get for the fact times the answer we get before we reach 1, we return the answer to the function. So here we have 2. I'll use the term case. So this will be my basis case. That's the smallest unit that will stop the recursion. Then this is my recursively. So the formula will be n times factorial. So the function is calling itself. Again, the function name is factorial, so it's calling itself and reducing by 1. So if it's 5, 4, next time it will be 3, 2, until this condition is true. If I reach n equal to 0, I will stop because I can't do anything. I'll return 1 because that is the condition for the basis step. So again, this is the whole concept of recursive, using factorial algorithms, using recursion for factorial algorithm. But what we want to know here is that in recursion, we have 2 cases, the basis and also the interactive, or in this case, the recursive. So we have another example, recursive exponential algorithm. So give a recursive algorithm for computing a to the power n, where a is a non-zero number and n is a non-negative integer. Now here, a to the power n means a times a times a, n times. But we are using recursion here. So first of all, I know that if I raise n, if n is 0, any value raised to the power 0 is 1. And that's the lowest unit n will reach. We don't need negative. So our basis case will be when n equal to 0, we'll return 1. Otherwise, we are going to return the value times a to the power n minus 1. Since we take a out, the n, if it's 4, it will be 3. Next time we take 1 out, it will be 2. Next time, until we reach 0, then we stop because 0 is the condition for our basis step. So that's why recursive section, we can see they say return a times the power, raised to the power a, by this time n minus 1, because we take 1a out. So it will be n minus 1. So next time we get the answer, next time it will be n minus 1 again, which is like n minus 2, 3, we go until n reach 0. And when we reach 0, the condition here will be true. Then we return the result. So the output will be a to the power n. So again, we know this concept already in arithmetic, but the whole thing we are learning here is how to design recursive algorithms. So here we can see the base case and also the recursive case. So in the base case, it's our condition that will terminate, will stop the recursion if the condition is true. And always the base case will be the smallest input we can get. We can go. So here, n should be 0. We don't want no negative, positive value. So n will go up to 0. Any value raised to the power 0 is 1. So we say when n equal to 0, we return 1. Otherwise, we return the value times the value raised to that power minus 1, because we take 1 value out already. So the power a n minus 1 will call itself until n minus 1 reaches 0. Till n reach 0, then that will meet this condition. Then we stop and return the result. Another algorithm is greatest common divisor. What we mean by greatest common divisor algorithm, we find this a lot in fractions. 2 values are given, maybe 2 and 4. We can say what is the GCD. GCD will be a number that is divisible by both numbers. So if I have 2, 4, the GCD will be 4, because 2 can go into 4, remain at 0. 4 can go into 4, remain at 0. So here we have an example saying that give a recursive algorithm for computing the greatest common divisor of 2 non-negative integers, a and b. But here we make sure that a is less than b. So for example, I have 2 and 4, not 4 and 2. So use the reduction. GCD a and b is the same as saying GCD B mod A. Remember, B is greater than A. So B modulus A, and then the A value. And the condition GCD 0 and then B will equal to B when B greater than 0. So maybe this will make us get the step well. So this means the lowest value for A always should be 0. And if A is 0, what will happen? B will be the answer. Because, for example, if I'm looking for GCD of 6 and 0, the answer is 6. Or 1 and 0, the answer is 1. So that's the basic step. When A equal to 0, return B. Else we return GCD B mod A. Remember the condition we have, A should be lesser than B. So actually I should say 24 or 06 or 010. So we said B mod A and A. So we have to, the function have to call itself doing this operation until A becomes 0. When A is 0, we return B, and then the final result will be the output of GCD A and B. Again, the whole concept here is using recursion method. We have our basis case, then we have our recursive statement or case. Also, we have the recursive binary search algorithm. So normally in the binary, in computer science, we have two common searching algorithm. One is linear search. Linear search means I have items in a list. Let's say we have A1, A2 up to AN, and I want to search a specific value. Linear search means I will start from A1 all the way to AN. For example, if I start from A1 and the item I'm looking for was A1, I will stop. I'll return what I'm looking, the position. Now, if I'm looking for A3, I will compare A3 with A1, it's not it. A3 with A2, it's not it. A3, oh, okay, we got the A3, then we return A3, we stop searching. So the worst case scenario is when we don't have the item, or the item we are searching is at the end of the list. Then we have to do a lot of comparison almost to the end. Now, with the concept of, so linear search is good for small lists of items, but binary search is good for large lists of items. But because with binary search, first we have to make sure the items are sorted. So when the items are sorted, we will look for the middle value. So we do some arithmetic operation, we get the middle value. Then when we get the middle value, we will compare with the right or the left of the items in between the middle, the item to the left of the middle, the item to the right. Whatever is true, we go to, for example, if the middle item is less than the search key, then we go to the left side because the left side have less item than the middle value. If the middle value or the search key is greater than, if the search key I'm looking for is less than the middle value, then we go to the left side. Now, if the search key I'm looking for is greater than the middle value, that means after the middle value, the items to the right of the middle value are greater than it. So we look for the. So this means in our first searching, when we get the middle value, we are going to divide the item in the list into two. One item will not be sorted no more. If it's greater, then we go to the lesser side. If it's lesser, we go to greater. Then we repeat the same item with the same step again. The new list, half of the new list, we find the middle, then we compare again. If it's greater, then we forget about the lesser side, then we find middle again. So you can see that binary, that's why it's called binary search. Always we divide the list into two. One part of the list we are not going to search. So this will save a lot of time. We don't need to do all the comparisons. So that's the whole concept here. Now we can use this. We can write this algorithm using loops, interactive, but we can also design it using recursion or recursive. And that's what we are doing here. So we can see that the first thing we do is the M is the middle value. So this I and J is like our index. Here we are assuming we are using array. So I and J can be our index positions. So I plus J divided by 2 will give me the middle value. Again, the index position, the middle. Now I'll say that, okay, if AM or X is equal to AM, then we return M. This means we have found the search key. The search key is the same as the middle value AM. So in this case, we return the M because our goal is not to return the search item. We know the search item. We just want to return the position, which is the index in terms of array. Else, we say, okay, if the search key, let's say the search key AM is greater than X, then we go to the greater section. So we go to, and also the middle is greater than the I. Then of course, we are going to the I and M minus 1. So which means we are going to search at the greater side. Because here we can see that AM is greater than S, or S is less than AM. And also I is less than M. Otherwise, the other way, if S is greater than AM, which means we're going to the lower side because AM is low. So in this case, it will take us to the lower side. So that's the algorithm. Now this is our recursion is what is happening here. This is our base. Our base means if we find the middle value, we are going to do comparisons. So the lowest comparison we can do is 1. When the search key is the same as the middle value, you stop. Otherwise, if the search key is less than middle value, so this means middle value is greater than the search key, then we go to the lesser side of the items. Now, if the middle value is lesser than the search key, and search key is greater than the middle value, then we go to the larger area from the middle. And these are recursive because we can see the function is calling itself. So they say we should prove the recursive algorithm if it's correct. So both mathematical and strong induction are useful techniques to show that recursive algorithm always produce the correct result. So for example, if they say we should prove that the algorithm for computing the powers of real numbers is correct, here we have the function name power. It takes a couple of arguments, A, non-zero real number, and N, non-negative number. Because this is power, A is like our base and N is our exponent. So we say that if N equal to 0, which means if the exponent is 0, any value raised to the power 0 is 1, so return 1. That's our base case. Else we return A times power A N minus 1, which means if I take one value from let's say I have 3 cubed. If I write 3 times 3 square is the same. So that's why we have N minus 1. In this case, to the power 3 minus 1. If I take 1, 3 out. Now, this is our solution. Now, we want to prove this is correct. So what we do, we use the mathematical induction on the exponent N because N is our input. So we have to use, most of the time again, always we use proving, we always use the input. So the input is N, and N happy to be the exponent because power A to the power N. So in this case, the basic step will be what? A to the power 0 is 1. The lowest unit for N will be 0, and the power is 1. For every non-zero real number is A, the base. The base will be a positive value and not 0. And the power A and 0, which means A to the power 0 is 1. So that's our basic step, the lowest unit. Now, in the inductive step, we say the inductive hypothesis is that the power ak is equal to a to the power k for all a not equal to 0. Now, we are assuming the inductive hypothesis, the algorithm correctly computes a k plus 1. Now, since power a and k plus 1 equal to a times power a and k, because we plus 1, we take 1a out. We use the a multiplied by power ak. So this is the same as saying a times ak, which will give us ak plus 1. So here we have proved that again, this recursive algorithm is correct, because we move from a to a plus, if the k is the exponent, so we get a times a to the power k is the same as saying a k plus 1. So next we go through the merge sort. Merge sort works by, again, interactively splitting a list with an even number of elements into two siblings of equal length until each sublist has one element. So what we mean is, actually we will see a diagram in the next slide, so we may go through that. But what we mean by merge sort is that if we have a list of items, we want to break it step by step until we have only one unit. Then we merge them together and putting them in correct order. So we may have each sublist is represented by balanced binary tree. And at each step, a pair of sublists is successfully merged into a list with element in increasing order. If your sorting is in ascending order, increasing order. Otherwise, we can also do decreasing order if your sorting is, the sorting you want to do is in decreasing order. So this is a very good example. We want to sort 824, 697, 10153. Well, there are so many sorting algorithms in computer science. Example can be from bubble sorting, we saw selection sorting, so many of them. But here we are using merge sorting. Each one uses different algorithm, but the goal of sorting is that we want to optimize our problem. So we need a sorting algorithm that do less comparison, which means it's more faster. So you can see that this is a list of the item in the diagram we are sorting. What do? We divide the sublist into two. One to the left, 82469, the other to the right, 710153. Then we do the same thing again. We divide the list into two sublists again. So we have 3 values here and 2. Then we divide it again, 2 and 1. Then the 2 we divide again. We are going to again divide the items until we have each individual item. So here we can see each individual item, 8, 2, 4, 6, 9, 7, 10, 1, 5, 3. Okay, now we have to this is where we will do our merging. We start the merging from the down. So first I have 8, 2. In the correct order, it will be 2, 8. So we merge it to 2, 8. 4 is by itself, I'll leave it. 6 by itself, I'll leave it here. 9 also, I'll leave it. But here we have 7, 10. So when we merge it, we still get 7, 10. And here we have only 1, 5, and 3. Now we reach this section now. This section means we have 2, 8, and 4. So we have to put it in order. So it will be 2, 4, 8. So we have 2, 4, 8. Here now we have 6, 9. So when we put it in order, we have 6, 9. And 7, 10 will be 7, 10 down. And then 5, 3 will be 3, 5, 10, 1 will be 1. Here we have the 7 also, so it will be 1, 7, 10. Now, if I want to reach this section, I have 2, 4, 8, 6, 9. So I'll put them in order. So I'll get 2, 4, 6, 8, 9, and that is 2, 4, 6, 8, 9. That's for almost all these. Then here we have 1, 7, 10. And also we have 3, 5. 1, 7, 10, 3, 5 to merge. So we get 1, 3, 5, 7, 10. So now we have the last part now. we have only two sublists now. We have to sort them and put them in order. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And that's what we have here. So merge sort, the first algorithm, first step, you want to break your item into one unit. Then later you merge them by putting them in the right positions. So in the recursive merge sort, we say here construct a recursive merge sort algorithm. Solution is we begin with a list of n elements L. So merge sort L equal to A1, A2 up to AN. Now we say that if n is greater than 1, then we divide the item into 2. You remember the diagram here, we have if the item is greater than 1, which means we have at least few items here, let's say 2 or more, we need to divide into 2. Always we divide the items into 2. When we are merging, then we combine 2 at a time. So that's why here again, we say construct a recursive merge sort algorithm. So we begin with the list of n elements. So again, the recursive merge sort, here again, they say we should construct a recursive merge sort, begin with the list of n elements. So these are the elements, A1, A2 up to AN. So first we said, okay, if n is greater than 1, we have a lot of, we have items. So we find the mid m. M will be, we divide the list into 2. We divide the list into 2 to m. Then we list L1, as we saw in the diagram. Then we have, let's say the left and right, L1 and L2, the items. So first, to the left will be A1 to AM, to the right will be AM plus 1 to AN, which is the total mean. Then we are going to call the function merge. That will merge the left and the right together through sorting. But here we say L is now sorted into element in increasing order. So this is the algorithm now. First, L is empty list. While L1 and L2 are both non-empty, which means we have an item, we should remove the smaller or the first element of L1 and L2 from its list. Then we'll put at the right end of L. Now, if this removable makes one list empty, then we'll remove all the elements from the other list and append them to L. Then we'll return L. So L will be our merge list with element in increasing order. Now, the complexity of the merge sorting algorithm is that we have two sorted lists with M element and N element. And this can be merged into a sorted list using no more than M plus N minus 1 comparisons. So example given here, we want to sort the item 2, 3, 5, 6, 1, 4. So that's our first list, our second list. So first list, we can see that 2, 3, 5, 6, 1, 4 is sorted. So the comparison 1 is less than 2. So next we have 2, 3, 5, 6. We merge 1 out. Then next we have 3, 5, 6 because we take 2 out. Then next we need 3 out. Then next we need the 4. So after we take the 4 out, we don't have anything in the second list. Then we'll bring the 5 and 6 together. So this is again after we break the element into smaller units, individual 1, 1. The process of merging the two sorted lists is what we just did now. So I have two sorted lists. I'll look for the lowest. For both two lists, the lowest is 1. The next lowest 2, 3, and then we keep going to the n. So let's see some example here. Here they say we should find f at 1, f at 2, f at 3, f at 4, f at 5. If f at n is defined recursively by f at 0 equal to 3 and f for n equal to 0, 1, 2. So first we need to find fn plus 1. And here they say it's negative 2fn. So this means if I'm looking for f at 1, it will be negative 2 f at 0, which will give me negative 2 times 3 because, again, f at 0 is 3. Now, if I'm looking for f at 2, I'm using the a again, negative 2 f at 1, because previously fn plus 1 minus 2fn, so it will be negative 2 times negative 6. f3, the same thing, negative 2 times f at 2. We have the answer, then f at 4 will be negative 2 times f at 3. Then f at 5 will be negative 2 f4. So we can see n plus 1, the previous n we are using, then times 3 plus 7. The same thing applied to, the previous one we are using times negative 2. So A, everything here is only times negative 2. Now in B, it will be 3 times the function plus 7. So in B, we know f at 1 will be the previous, here will be the previous f at 1, then f at 0 plus 3. So 2 times f at 0 plus 3, which will be 3 times 3 plus 7, 16. Now f at 2 should be f at 1 times 3 plus 7. So f at 1 times 3, the function is fn, 3 plus 7. So we know f at 1, we just find the result. The result is 16. So we say 16 times 3 plus 7. Then let's do one more. F at 3, B, 3 means we have 2. So it will be 3 times f at 2. F at 2, we just find the answer right now. So we plug in the answer, which is f at 2 plus 7. It will give me 3 times 55. Then plus 7. The same thing applies to the B, C, D. Let's say if we use C. C, we have fn plus 1, fn square minus fn minus 2. So this means if I'm looking for f at 1, I need f at 0 square here, which will be 3 square. So let's go B. So we get 3 times 3. No, actually, we are doing C, sorry, C. So we see that we get f at 0 all square minus 2, f at 0 again minus 2. So that will give me 3 square minus 2 times 3, then minus 2, which will give me 1. Now f at 2 will give me f at 1 square, which is f at 1 square, and f at 1 is 1, so we get 1 square, minus 2 times f at 1, which is 1. Then again, we do the calculations. So again, let's do only one for D. F at n plus 1, 3 to the power f at n divided by 3. So if I'm looking for f at n plus 1, it means if I'm looking for f at 1, then it will be 3 to the power f at 0 divided by 3. So let's see the D here. F at 1 will be 3 f at 0 divided by 3. So this will give me 3 to the divided by 3. And my answer will be 3. The same thing for 1. Since now I know f at 1 is 3. So I'll say 3 to the power 3 divided by 3. So next is tracing algorithm 1 when it's given n equal to 6 as input. The algorithm 1 is finding the factorial of a number. So here we need to show the step used by algorithm 1 to find 6 factorial. So first, we know that 6 factorial is the same as 6 times 5 factorial, which means we get n times the function n minus 1, which is 6 times 5 factorial. Factorial is the function, so we have to say the function n minus 1. Then we can use the same recursive step repeatedly to write 5 factorial, which will be 5 times 4 factorial. 4 factorial will be 4 times 3 factorial. 3 factorial will be 3 times 2 factorial. Then 2 factorial will be 2 times 1 factorial. And the last 1 factorial is 1 times 0 factorial. 0 factorial is 1. And working back through the step, we see that 1 factorial is 1 times 1 equal to 1. Then 2 factorial is 2 times 1 factorial, which gives us 2 times 1. Then 2 and 3 factorial will give me 3 times 2 factorial, etc. So we keep doing it until we reach 6. So 4 times 6 is 24. 5 factorial will be 5 times 4 factorial, so it will be 120. Then 6 factorial will be 6 times 5 factorial. 6 times 120 will give me 720. So the final result will be 720. So next example says we should give a recursive algorithm for finding the sum of first n positive integers. So here we can say the sum of the first n positive integers is the sum of the first n minus 1 positive integers plus n. So we write the function into the sum of first. So we are starting the n and also the positive integer. So if n equal to 1, then we return 1. Because 1 is the smallest unit. If n is 1, we return 1. Otherwise, we return the sum of first n minus 1 plus n. So again, this will be our conclude. Okay, we have one more example. So here also we say give a recursive algorithm for finding the string wi. The concatenation is the joining of I copies of w when w is a bit string. So we're using recursion again. So we have the function name power. And our basis case will be when I equal to 0, we return lambda. When I equal to 0. So that will be our base case. Now, as we return w concatenated with power wi minus 1. So that will be the conclusion of our lectures on recursive algorithms. We were able to go through some few examples also. So again, if you have any question about the course in general or question about the lectures, again, you can send me an email. Thank you.